You're watching a Channel 98 NBISD TV production.
Hey, welcome to another brand spanking new edition of That Geometry Show. We're broadcasting live on tape from the basement here at the New Braunfels headquarters. As always, I'm your host, Kevin Corpy, and today we're going to be doing a lesson that's going to be dealing with some special parallelograms. We're going to be talking about rectangles, squares, and rhombi. That'll keep you here. Anyway, get on the internet and download those worksheets from www.newbraunfels.txed.net. Get them in front of you, get a sharp, pointy pencil, ready to go, and let's do some math together. Okay, lesson 16 today is going to correspond with your Glencoe Geometry textbook, chapters 6.3 and 6.4. And as promised, we're going to be talking about rectangles, squares, and rhombi. Now, to kind of review from previous episodes, we need to go over some things here. So we need to remember that blank are closed geometric shapes. The most general form of a geometric shape that's closed is a polygon. Okay. Now, special types of polygons are the four-sided variety, and we call those quadrilaterals. Quad meaning four and lateral meaning side, so four-sided polygons. Now, even more specific than that, special quadrilaterals whose pairs of opposite sides are parallel to each other are called parallelograms. Okay? Now, you might think that that's getting pretty specific right there, but today we're going to get even more specific, and we're going to talk about three special types of parallelograms, okay? And those are rectangles, squares, and rhombi in that particular order. So, to the first formal definition, most of y'all are out there are really familiar with what a rectangle is. But here's the formal definition. A rectangle is a quadrilateral, meaning it has four sides, and it's closed. All the sides are connected, and it has four right angles. That means that this is a right angle, this is a right angle, and this is a right angle. And remember, right angle means that they equal 90 degrees. So, that's the only requirements for a rectangle. Four sides, all the angles are 90 degrees. Now, because it is a parallelogram, remember we can put notations here for opposite sides being parallel. We put the little arrow marks, so that's a nice review. Single arrows there, meaning that these two sides are parallel, and double arrows here, meaning these opposite sides are parallel. So it is a parallelogram. Okay? Now we're going to look at some special properties of a rectangle. We can draw the diagonals of a rectangle. Basically taking from one corner here and drawing a line to the opposite corner, that creates a diagonal. And there's two diagonals in a rectangle. Now rectangles' diagonals have the special property that they are congruent, which means they're the exact same length. Okay? Now let's review also from just parallelograms in general that aren't necessarily rectangles. We know in any parallelogram that the diagonals bisect each other. So we know that segment AE is equal to segment EC, or congruent to. They have the same measure, and segment DE has the same measure as segment EB. But in a rectangle, we know that the actual diagonals are the same length. So we know that AC is congruent to DB. Now, we know that this is congruent to that right there. They have the exact same length. And they bisect each other because it's a parallelogram. So what that means is, since it's a rectangle, we know that AC is congruent to BD, and this forms two sets of congruent isosceles triangles. Let me outline those for you so you can see them a little bit more easily. Triangle AED, which is this one here, is going to be an isosceles triangle that's congruent with this one over here. Triangle AED is congruent to triangle BEC. Remember, the notation of the letters is important. A corresponds to B, so AED congruent to BEC. We can also say that triangle AEB, this one up here, triangle AEB, let me write it down here, triangle AEB is congruent to, the corresponding side down here would be triangle DEC. So those four triangles are not congruent to each other, but the opposite triangles that are isosceles are congruent to each other. Okay? Let's look at an example with that. Here we go. In rectangle ABCD, we know that the measure of segment AC, which is this entire diagonal here, is 24 units, and the measure of segment DE, which is this half diagonal segment, is 2x minus 8. What we want to do is we want to find out what x is. Well, because it's a parallelogram, we know that the diagonals bisect each other, so we know that this is equal to that. Well, if the whole thing is 24, and these have to be equal, then each of the half segments have to be 12. So we know that the measure of segment AE is equal to the measure of segment EC, which is going to be half of 24, or 12 units. Okay, so we know that this is 12. Now, because it's a rectangle, they not only bisect each other, but because the diagonals are the same length, all the little half diagonal segments are congruent to each other. Remember, this is an isosceles triangle, so this is congruent to this. So we know that 12 has to equal 2x minus 8. And that's where we get the information to set up our little algebraic equation. So we know that 12 equals 2x minus 8. And I'll collect the 8 on the left side by adding 8 to both sides. And I get 20 equals 2x. And dividing both sides by 2, I get x equals 10. And that's the answer. It's right there. It's choice D. Okay? So again, in a rectangle, we know that all the half of the diagonal segments are congruent to each other. Another example. In rectangle WXYZ, we know the measure of angle 1. Okay, so we're dealing with angles now. This one right here is 40 degrees. We want to find the measure of angle 2 right here. Okay? Well, how are we going to do that? We know that this is a rectangle, so we know that it forms isosceles triangles. So this measure has to be congruent to that measure. This is an isosceles triangle. Remember from a previous episode that if these are the two congruent legs, then the opposite angles, which are called the base angles, are congruent to each other. Okay, so we know that the angle 2 has to equal the measure of angle 3. Well, we also know that the sum of all the interior angles of a triangle have to equal 180. So I know that the measure of angle 2 plus the measure of angle 3 plus my other angle, measure of angle 1, which is 40, has to equal 180. Well, that leaves, if I subtract 40 from both sides, that leaves 140 for the sum of my two angles, angle 2 and angle 3. But they have to be equal to each other, right? So if these are the exact same size, then they're each half of 140, or they're both 70 degrees. So 70 degrees is the answer, and that's choice B right there. Okay? Now the other congruent isosceles triangle to this one would be this opposite one over here. Okay, but we just worked in this side right here. We could have worked equivalently with this triangle here and gotten the exact same results. Okay, so rectangle, remember, the diagonals are the same length, which means when they bisect each other, we get 4 little sets of congruent half diagonal segments. Rectangles. Okay, moving on. The next special parallelogram we're talking about today is the square. Now here's the definition of a square. The square is a quadrilateral, 4 sides, with 4 right angles, just like the rectangle. That means that this is a right angle, this is a right angle, this is a right angle, and that's a right angle. Now, what differentiates a square from a rectangle is this last little piece of information. We have to have 4 congruent sides. In a rectangle, the opposite sides were congruent, but in a square, all the sides have the exact same measure. So they're all congruent. Okay? So we know that AB is congruent to BC. I'm sorry, not BC. That should be a BD. It's congruent to DC. It's congruent to CA. So there's a typo right there. Okay, that's a BD. Now, squares have all the same properties of rectangles and some additional ones to boot. And that's because all squares, and this is kind of interesting, all squares are rectangles. Did you know that? I'll put an exclamation point, maybe even 2 of them there. That's pretty exciting information. Now, not all rectangles are squares, but every single square is a rectangle, because remember, the rectangle just said it has to be a quadrilateral with 4 right angles. Well, square definitely fits that description, but the square has some additional information as well. So all squares are rectangles. All right, now here's the additional properties that squares have. The diagonals intersect each other, and they do bisect each other, just like any quadrilateral. And the diagonal segments are equal to each other, like in a rectangle, but in a square, they intersect each other at right angles, which means the diagonals are perpendicular to each other. Now what that means then is that the slopes of the diagonals are negative reciprocals of each other. All slopes that are perpendicular are negative reciprocals of each other. Okay? So they intersect at right angles. The other nice thing about squares is that they bisect a pair of opposite angles, which means this angle right here, which is originally 90, okay, remember it had 4 right angles, is now cut in half by the diagonal, so that this angle is congruent to that angle, and this angle is congruent to that angle. And if it has to be 90 degrees, then half of 90 is 45. Well, that has to be true all the way around. Same thing on this side. So all of these angles right here in the square are congruent to each other, okay? Which basically means I have 1, 2, 3, 4 congruent half diagonal segments with equal angles. We get 4 congruent isosceles triangles, not just 2 sets of congruent triangles like in a rectangle. All 4 of these triangles in the square are congruent isosceles triangle. And that right there is quite a bargain. What a deal. Okay? Let's look at an example now with squares. Here we go. We got a square appropriately named MATH. What we know is that segment KA has a measure of x squared plus 1. Let's identify it. KA is here. I like to draw on the diagram, call that x squared plus 1. And we know that KT, which is this one right here, is 3x plus 11. We want to find the value of x. Okay, so how are we going to do that? We know it's a square, so we know that these are right angles. We know that they intersect at 90 degrees. So that makes this triangle a right triangle. Okay? Is that going to help us, though, in a right triangle? In right triangle, remember, we can use the Pythagorean theorem if we're talking about side lengths. But we don't know anything about the length of this. So we're going to have to find a way to relate these two sides to each other. Well, remember, in a square, the diagonals bisect each other, so I know that this is equal to that. But because it's a square, we also know that this and this bisect each other, and they're actually the same measure as the other ones, all the way around. Okay? So these two are actually equal to each other. So I can set up a little equation here. X squared plus 11 has to equal x squared plus 1, my bad, equals 3x plus 11. Now, if I group everything on one side, because I have a squared term, a non-squared term, and some numbers, I want to group everything on one side. So I'm going to call that x squared. Write it in decreasing order. I'll have minus 3x. And if I subtract 11 from this side, I end up with negative 11 plus 1, which is negative 10, equals 0. So this is a quadratic equation now that I have to solve. And we haven't seen one of these this year. This is a nice algebra problem. The first method that we tried to solve this by is by factoring. So we're looking for factors of x squared. Well, that's going to be the square root of x squared, or x and x. Negative 10 is our target product. Negative 3 is our target sum. So we're looking for factors of negative 10 that add to negative 3. Now with a little trial and error, you'll come up with 5 and 2. The product of that is 10. And since we want it to be a negative sum, we need our larger number, negative 5, to be the negative, and positive 2 here. So a quick check will give us negative 5x on the inside, positive 2x on the outside, which adds to negative 3x. Now the zero product property tells us if we have things multiplied together equaling 0, I can set each of them equal to 0. So x minus 5 equals 0, or x plus 2 equals 0. And then two little algebraic equations solving, I get x equals 5, or x equals negative 2. Now x in this diagram up here is actually a component of a length. So it doesn't really make sense to talk about negative lengths. Although plugging in a negative 2 will not give us negative side lengths, we could have a dimension of x somewhere in other parts of the square. So in this case, x equals negative 2, because we're talking about lengths, doesn't really make sense. And so the best answer of the final 2 is just x equals 5. And that's the answer to the question. Okay? All right, it's time for a break. Let's watch some of those public service announcements, and we'll be right back.
There comes a point in your life when you realize you're not a kid anymore. Suddenly, you have to make decisions. You have to make choices every day. This is the time when you define yourself, or you let others define you. You quickly learn that there are two ways to go: under the influence or above the influence. I am above the influence.
Welcome back. let's get on to those rhombi, shall we? Okay, the last special parallelogram of the day is the rhombus. Nice word, rhombus. A rhombus is a quadrilateral, of course. It has 4 sides, and it has 4 congruent sides. So unlike the rectangle and the square, the angles of a rhombus need not be right angles. Okay, but other than that, the properties of a rhombus are very similar to the square because it has 4 congruent sides, which means that this side is congruent to this side, is congruent to that side, is congruent to that side. But notice how this kind of rhombus looks like it's a square that is kind of fallen over, like a poorly built shed that's leaning. Okay, the angle up here is no longer a right angle. That's why it's a rhombus. Okay, but it still has 4 congruent sides. Now, let's look at the properties of a rhombus. It is a quadrilateral, so it shares all the same characteristics that all quadrilaterals do. The diagonals bisect each other. So we know that because it has 4 congruent sides, segment LO is congruent to OV, is congruent to VE, is congruent to EL. Okay, that's very similar to a square. Also similar to the square, we know that the diagonals bisect each other at right angles. Remember, this right here is the symbol for perpendicular. So LV, that diagonal, is perpendicular, we say, to OE. So that means that this and this are right angles, 90 degrees. That's pretty cool, similar to a square. Now, also similar to a square, we know that the diagonals bisect a pair of opposite angles. So we know that this angle here, L, whatever it is, it's not 90 degrees necessarily. It's cut in half by this diagonal. So I know that the measure of angle 1 is equal to the measure of angle 3, and the measure of angle 6 is equal to the measure of angle 8. I also know that these opposite other angles over here are also bisected by this diagonal. So the measure of angle 5 is congruent to the measure of angle 7, and the measure of angle 2 is congruent to the measure of angle 4. Now, this is different from a square in the respect that these angles here on this diagonal that are bisected are not congruent to these necessarily, but they are congruent to each other. Okay, very important to get that straight. All right, here's an example with the rhombus. In a rhombus, EFGH, we know that the measure of angle 1 is 57 degrees. So I'm going to draw that on here, 57 degrees. And we know that HE, the length of the segment, is 13. So that's this here. HP, which is right here, is 12. What is the measure of angle 2? So we're looking for this right there. Okay, so how are we going to attack this problem? We know it's a rhombus. So what do we know about a rhombus? Well, we know that all the sides are equal. So if this HE is 13, we know all of these are 13. Is that going to help us? Maybe, maybe not. What else do we know about a rhombus? We know that the angles opposite each other are bisected. So if this is 57, we know that this is 57, and so are these two down here. Is that going to help us? Maybe, maybe not. We also know that the diagonals intersect at right angles. So this is a right angle, which makes this right here a right triangle. Now, because we're trying to find the measure of angle 2, and we know that this is a right angle, we know that it's 90 degrees and this is 57. So remember, the sum of all the interior angles of a triangle have to equal 180 degrees. So we know the measure of angle 2 plus 57 degrees plus the right angle 90 degrees has to equal 180 degrees. Is that going to help us? Absolutely. If I subtract 90 from both sides, I basically know the measure of angle 2 and the measure of angle 1 have to be complementary. So solving this equation, I get the measure of angle 2 is equal to 33 degrees. So that's just using the sum of the interior angles. But we needed to know this was a right angle, and that's where the rhombus came in. All right, next part. We want to know what is the measure of segment PE. Okay, so that's going to be this segment right here. We're trying to find out what this length is. Well, how are we going to do that? We still have this right triangle, and we're trying to find a missing side length in a right triangle, and we know the other two sides, 12 and 13. So if you think back into your past, you can pull out of your bag of tricks here the Pythagorean theorem, because the Pythagorean theorem was a theorem that allowed us to work with side lengths of a right triangle. If we know any two of the three sides, we can find the third. So we need to carefully figure out which one's the hypotenuse. HE is the longest side. It's opposite the right angle, so it's the hypotenuse. So we can set it up as segment HE's measure squared has to equal PE squared plus HP squared. Okay? Now I can fill in what I know. I know that HE is 13, so 13 squared equals, PE is what we're trying to find, so that's still PE quantity squared, the measure of the segment squared, plus HP is 12, so that's 12 squared. Now, these are squares that you should have memorized. If not, a calculator is there to help you. 13 squared is 169, and we still have PE quantity squared plus 12 squared is 144. So now if I subtract 169 minus 144, I get 25 equals PE squared. Now to solve for PE, we take the square root of both sides, and I get PE equals, or the measure of PE, is plus or minus the square root of 25. Remember to take both positive and negative roots when you're taking the square root. And that's going to give us positive 5 or negative 5. Now, we want to interpret those answers. Because, again, we're talking about the length of a segment, negative lengths don't make much sense. So that's not a reasonable answer. So in our problem, the answer is 5. Okay, now it's time for the part of the program, my favorite part, called the Say What? Okay, and this is a chance for us to kind of review and kind of get all these things distinctly separated because they're very, very similar. A lot of overlapping characteristics, but they're subtly different. Okay, so let's start off by answering some of these questions. A square is a blank. Square is a what? Look at the answer choices. Is a square a rhombus? Is a square a rectangle? Is a square a parallelogram? Or is a square all of those? Well, remember what I said earlier, that every square is a rectangle, okay? Because a rectangle just says quadrilateral with 4 right angles, and a square definitely has that. So a rectangle would fit. But because one of the answer choices is all these, we need to consider the other two. Is a square a parallelogram? Well, a parallelogram is just a special quadrilateral with opposite sides parallel to each other. And yes, a square is a parallelogram because this side is parallel to that, and this side is parallel to that one. So choice C is also correct. Now, without even knowing that it's a rhombus, it has to be choice D because we have 2 correct answers. So let's figure out why a square is in fact a rhombus. A square is a rhombus because remember, a rhombus just says it has to be a quadrilateral with 4 congruent sides. Well, a square is a quadrilateral with 4 congruent sides with the additional aspect that it has 4 right angles. So a square is a rhombus. The best answer is all of these. So look at Mr. Square. This is going to be cool. A square is a rectangle. Every square is a rectangle. And every square is a rhombus. That's pretty cool. But not every rectangle is a square, and not every rhombus is a square either. But a square is both of those. Okay, moving along. What is the best description for a quadrilateral, 4 sides, with 4 right angles? Okay, well, let's go through the choices. Square, parallelogram, rhombus, and rectangle. We know that a rhombus doesn't necessarily have to have 4 right angles. That's that leaning shed, remember? So that can't be an answer choice. A parallelogram, well, a parallelogram just says opposite sides parallel. A rhombus is a parallelogram, and we already know a rhombus doesn't have to have 4 right angles, so that can't be an answer choice. So we're left with square and rectangle. Now a square and a rectangle, both, in their description, have 4 right angles. So we're looking for the best description. Okay? Is every square a rectangle? Is every rectangle a square? Notice the description up here doesn't say anything about the side lengths. So if we go with square, we're kind of limiting ourselves to having 4 congruent sides. So what we want to do is we want to go with answer choice D. A rectangle is the best description of what we have, just a quadrilateral with 4 right angles. That'll leave us room for having possible squares, whereas if I went with square, then I couldn't have rectangles. So going with rectangle kind of gives us more opportunities, more inclusion there. It's more general. So the answer is D. All right, which statement is false? Let's go through these and determine if it's true or false. We're looking for the incorrect statement. Every rhombus is a quadrilateral. Well, a rhombus is a special type of quadrilateral. It has 4 sides, so that's a true statement. Every rhombus is a parallelogram. Or remember, we're looking at 3 special parallelograms today, rhombi, square, and rectangle, so that's true as well. The opposite sides of a rhombus are parallel to each other. Every rhombus is a square. Well, if you can find one rhombus that isn't a square, namely any of the ones that we've been looking at, that one right there, so that these sides are congruent, it's not a right angle up here, here, here. This is a counterexample. A counterexample basically is an example that disproves a statement. And so we have found a rhombus now that's not a square, so that one can't be true. Every square is a rhombus? Absolutely. If you draw a square, we know it's a rhombus because a rhombus definition is basically a quadrilateral, 4 sides with 4 congruent sides. So a square is a rhombus. That's true as well. So the answer is choice C. Number 4. The most specific description of this quadrilateral below is a what? Okay, it's a quadrilateral. It looks like these marks indicate that we have 4 congruent sides. So a quadrilateral with 4 congruent sides. Was that a square? Well, that could have been. I'll put a little check and come back to it. A rhombus, 4 congruent sides? Yes, that was also true. A rectangle didn't say anything about side lengths. A rectangle said 4 congruent angles. A rectangle can have 4 congruent sides, but not in general. And again, a parallelogram, in general, doesn't give anything about the side length. So we're down to a square or rhombus. Now notice this diagram, the way it's drawn, it does not appear that this is a right angle or this is a right angle. But more important than the way it's drawn, there's no marks indicating that they're right angles or no measurements given that it is a right angle. So we can't assume that they're right angles. So the best we can do is just to say that it's a quadrilateral with 4 congruent sides, and we'll go with a rhombus there. Okay? Now, that leads in nicely to this last example. Choose the most precise description for this figure shown. Okay? We have 6, 6, 6, and 6 meters all the way around. It's a closed quadrilateral with all sides congruent. So again, like above, it could be a square or a rhombus. Parallelogram is not specific enough. Quadrilateral is not specific enough. We can actually go to a square or rhombus because the sides are equal. Now, they tell us that this angle here is 90 degrees. Will that help us narrow it down to a square or rhombus? If you're leaning towards square, be careful. That's the trap here. Because a square says that these angles up here have to be 90 degrees, not the intersection of the diagonals. And remember from the definition of a square and a rhombus, some of the special properties, on both of those geometric figures, the diagonals intersect at right angles. So we still have the possibility of a square or rhombus. Now, here's the other trap. The way that this diagram is drawn, it's drawn to appear to be a square, that these look like they're right angles. But again, if there's no little mark here, okay, that little box like we have here, if there's nothing drawn there and there's no measurements indicating that they're right angles, we can't assume that they're right angles. And so again, the best we can do is say that it's a rhombus. Now, some of you out there are probably having a hard time seeing that. So let me give you another example that kind of has the same information, and I think you'll be convinced that best we can do is a rhombus. If I look at this diagram right here, we'll call it parallelogram CARE. So take parallelogram CARE. This has the exact same information. This is 90 degrees here, 90 degrees here, and we have all the sides equal. That's exactly the same scenario on the last example. But I drew this one to an extreme case. I don't think anybody out there would dare call this a square because this angle here is not 90 degrees. It's actually an acute angle. And this one here is not 90 degrees. It's an obtuse angle. So sometimes taking a diagram like this that doesn't have any markings and drawing a very extreme case can help convince you that it's not what it appears to be. Well, that brings us again to the close of another lesson on geometry. But I hope y'all learned something, and I hope you had as much fun as I did. Until next time, I'm Kevin Corpy, and I will catch you on the flip side.